Hello, my name is Artemmen, I'm from Primeur magazine, and we are talking here with representatives from several European Exascale projects. So we have Filippo and Estella, and Filippo is from the MontBlanc project and Estella is from the DEEP-ER project. So Estella, can you please tell a little bit broad about the goal of the DEEP-ER project?
Sure. So, in fact, we have two projects, the DEEP and DEEP-ER projects. They are both European Exascale projects. What we are doing is we propose a new architecture, an innovative architecture, which is hybrid, but is a bit different to what we know today. So we propose the so-called cluster booster architecture. We build a booster based on Intel Xeon Phi processors. We put all these processors together into their own network, which is called Extol in our case, and we in this way operate accelerators in an autonomous way. So this cluster booster approach allows us to map the scalability levels of the applications into the hardware. So you analyze your application, you see where are your highly scalable code paths, and you put them onto the booster. The low scalable code paths, you leave them onto the cluster. Then in the DEEP-ER project, we look more into the I/O and resiliency aspect. So we are looking into new memory technologies. We are enhancing this standard cluster booster architecture with new memory technologies.
Okay, thank you for the explanation. And can you tell a little bit the same about the MontBlanc?
Yes. So we have similar structure. So we have MontBlanc and MontBlanc 2. So in MontBlanc 1, so the main objective is to exploit, say, embedded and commodity technology, means the commodity that we have in our smartphone and tablets for doing scientific computation. And so this is a general idea of the project and of both projects. And then, say, in MontBlanc 1, the main target is to build a real prototype. And we actually have it installed in Barcelona, at the Barcelona Supercomputing Center since February this year. And we actually have part of it at the student cluster competition, where 6 students are doing the challenges of the student cluster competition with the MontBlanc prototype. So from the prototype, we learn for next generation architecture based on basically ARM chips, and we also have say a set of applications that are real scientific applications that are tested on this new architecture. Then, as I said, in MontBlanc 2 we decided to explore other topics that were not covered in MontBlanc 1. For example, the resiliency topic, that is a key challenge for exascale systems. And we also improved our tool support, because program this kind of say weird architecture sometimes requires support of tools for debugging and for performance analysis. So we have a full coverage of tools within the project.
Okay, thank you. So thanks. So you're here on an Exascale booth, also together with other projects. And how important is the collaboration for you with all other projects in say first in Europe and then also internationally? Do you also collaborate internationally? But let's first say from how important is collaboration in Europe for you?
So, just the fact that we can be here, have a booth to show our projects, this already helps to make it being in a collaboration with more projects. We can, let's say, be more active, more present, have a higher visibility when we are more people involved. Of course, also from the scientific point of view, these other projects which look at very different aspects, they look more into the software parts, more into applications. For instance, we have a project which is focused on industrial applications. It opens up opportunities which were not considered or not inside the specific projects that we have, for further collaboration. So we can identify points where we kind of address the same kind of problems, the same kind of issues, but with different approaches, and we see, okay, where things are complementary, where maybe some approach is more efficient than the other.
Yeah, I think the key point is sharing knowledge of what we are doing, right? Because we basically all know about the challenges, but having a place like this booth means that you are sharing your way to tackle these challenges, right? And if you are strongly focused just in your project, sometimes we don't even know what's projects that are more or less going in the same direction do, right? So these are the kind of events that allow us to share what we are really doing and the achievement, the results, and this is a key point. And also the events that we are going to do together are say opening up the results to a larger community. For example, the workshop that we are going to have in the end, say on Thursday this week. This is basically this idea of opening our results to a wider community to show where Europe is going in this race to Exascale, but also in a fine-grained way show each of these projects what they are really doing every day and what they can really achieve.
Do you also collaborate internationally? I mean, with Japan or the US or other countries?
Well, we try to use these events, the same here at the ISC, also the supercomputing in the US, really to networking, to look at other people looking on doing maybe similar or equivalent things on the other continents. So that's the platforms what we use most for collaboration. We have also, at least in our case, through our institutes, for instance, the ULIC Supercomputing Center and the other institutes which are involved in the project, they have also their own collaborations with different institutions all over the world. Of course, we use also these platforms to disseminate the efforts that we are doing and to share experience in the same way we do in Europe.
Yeah, I mean, it's important that basically all the partners are international player within Europe, but they all have contacts worldwide. So we constantly have contacts all over the world, and there are events like this or events like supercomputing that allow us to open to this to this community, to a worldwide community. In the case of MontBlanc, for example, we have this end user group that is a dissemination tool that we use for say we have this prototype that I was talking about before. And there are companies that are outside in the world, not only in Europe, that want to try this kind of platform. So we offer these companies access to our platform, and we do a sort of exchange, or we exploit this win-to-win situation. We have the prototype, they have the application, so we collaborate in this sense. And this is, it has no border basically. And that's the kind of things that we do in this kind of events, actually.
Okay, thanks for the introduction. So let's now look at some of the results. Thank you. We are here now with Yuri, and he will explain a little bit more about the technology behind the DEEP-ER project.
Yes, thank you. So, while the DEEP booster prototype is already running in its system, in the DEEP-ER project, we're still investigating in new technologies, not only by extending the current commodity devices, but also investigating in new research areas, of which one is the network-attached memory. I will explain to you now. So first of all, in the DEEP-ER project, we use the high-performance interconnect Exascale. With Exascale, you can connect nodes in a 3D torus switch list. That is, you have 6 links on the side where you can span the torus. There's another 7th link where we are able to plug additional devices to it. That is, for example, another hierarchy of memory. So what we investigate in is the so-called network attached memory. The network attached memory will consist of an FPGA and a 3D stacked DRAM hybrid memory cube. You will then be able to plug the network attached memory directly to the external network. So now we're not just extending the network by additional level of memory, but also we will be able to implement specific functions and the ability to process memory in the FPGA. So when there's a remote host, you don't need, if you want to do an operation on the far memory, which is the hybrid memory cube, you don't need to transfer the data back and forth through the network, calculate it and write it back to the HMC. Instead, you send a small descriptor that is a very small packet through the external network to the network attached memory. It will perform all the calculations and, if desired, will send you the result back. These operations can be simple global sums, reductions, and also vector processing, for example. Another application for the network attached memory, for example, is checkpointing. If your system fails, you need a checkpoint, and with the hybrid memory cube, which delivers a magnitude of more bandwidth than traditional DDR systems, you will be able to get the restart checkpoint as fast as possible. So, as with any other memory technology, you need a memory controller to talk to the HMC. Because HMC is rather a new technology, we have developed our own HMC controller. So, let me show you what we achieved. So, what you see here is a Xilinx FPGA in the middle and a hybrid memory custom board that we have developed on our own. It is built for evaluating and for verifying the operation of our own HMC controller. What's good to know is that the controller, the HMC controller, is made open source. So if you want to have it, you can download it and you can use it for no cost. Thank you.
Okay, thanks Yuri. We now move on to the MontBlanc project. Thanks.
Thank you.
So we are here now with Filippo at the MontBlanc booth, and he will explain a little bit more about the technology.
Thank you. Yeah, so here we are, and we have the MontBlanc prototype actually in real life. So what I have here in my hand is a note card of the MontBlanc prototype. Means the form factor, that's my business card. It's a credit card form factor basically. And what do we have here is a system on chip that is including dual core ARM Cortex A15 plus a Mali GPU. Everything is embedded here, and then we have RAM, so memory, and then some local storage and some network. So basically what we have here is capability of a server, but in a very small form factor. So what we do then is to integrate 15 of these note cards in a blade. I was actually saying bool blade because bool is part of the consortium of the project, as well as ARM and other research centers. And so we use the bool technology, say from here to scale up to 2 racks. We have 2 racks of this kind of technology. What is really interesting, actually, I mean, as I said before, this prototype is installed at Barcelona Supercomputing Center, so we are using it. And one important point is, in order to investigate the energy efficiency, is to be able to control the power consumption. So here we have a power monitoring that is at level of the note card, so we can really monitor every single note card from 1 to 1080. So we can have fine-grained power monitoring, and also we are collecting all the power data, temperature data, so everything that we can gather at node level, say, and we are collecting it in a database. So this means that we can do sort of data analysis. You can submit the job in our cluster, and you can do data processing post-mortem. So you run your job, you finish, you get your job ID, you get the starting point, ending point, and you get the energy to solution, right? And this is a key point. The amount of energy that you are using in an application, and you can also have the energy in different implementation of the same application. So in this sense, we can investigate how efficient are different implementation, or how efficient, for example, is the programming model that we are introducing and using in this kind of architecture. Actually, concerning the programming model, that's say a piece of software that is developed in the Barcelona Supercomputing Center. Is called OMS, and is basically a forerunner of OpenMP4, right? And the idea is to have a task-based programming model in which you find you use data dependencies in order to schedule tasks. So that's basically what we have running, and what we are investigating every day. And we are really excited because we can really control a lot of parameters, so we can measure, and having measurements then have say a more clear understanding of where this technology can say lead in our investigation. Thank you.